Today I'm going to present an overview of geophysical methods, electrical resistivity and self-potential, and their usage in agricultural mapping and monitoring. Geophysics studies natural physical fields which exist on Earth. Those can be gravitational fields, thermal fields, hydraulic fields, and electrical and electromagnetic fields. Those fields influence all the matter and all the living organisms on Earth, including soils and plants, which are the main interest for agriculturals, of course. But the problem is that the scale of measurements in agriculture is much smaller than in conventional geophysics. So, to use electrical geophysical methods in agriculture, we can bring to our studies a lot of benefits. First of all of those methods are non-destructive. So we don't need to collect soil samples, we can just take measurements from the soil surface. Also, methods are very fast. But, however, all the methods are non-direct. They don't directly measure the properties of interest of agriculturals, such as soil bulk density, for example, or pH, and so on. They measure parameters of electromagnetic fields, such as natural electrical potential, also called self-potential, electrical conductivity or resistivity. That's what we are going to be talking about in depth, and those about two of those properties. They also can measure induced polarization and dielectric constant, but those properties were not very popular in agricultural applications. However, as I told, measuring self-potential with standard geophysical equipment in agriculture is very difficult. You can see such a big electrodes which need grounding and pouring conductive solution around them. The equipment is very big and difficult to apply to their soil samples or plants. That's why in our studies we used and adapt medical mini-electrodes that can be used with a land mapper device and measure electrical potential between plants and soil. What do those self-potential and electrical resistivity or conductivity measure the differences? And those differences exist in soils because there is a difference in density of mobile electrical charges in soils. And so those electrical parameters relate exponentially with amount and mobility of electrical charges, according to Boltzmann's law of statistical thermodynamics. That law presents that the density of charges and their energy is exponentially related with the potential and the absolute temperature. And Nelson in 1972 adopted those for soil water, for example. We can follow through the derivation and we'll see that soil water content is exponentially related with electrical resistivity and can be any other property as well. So in plants, they react to atmospheric electricity. There was shown the electrotropism of plant roots. It means the root grows toward negative electrical potential, and this is unrelated of gravitational effect, as was proven by NASA in growing plants in outer space. Also, there is a micro potential exists due to differences electrical charges in plant cells or animal cells. So basically, everything around us has electrical potential differences and has electrical properties. For example, we measure natural electrical potential in the rose canes in greenhouse rose production. We'll see that electrical potential in millivolts was kind of stable, a little bit high during the active growth, and then when the rose canes were ready for production, for the cutting the canes for propagation, the potential drops. And for the production, for the bouquets, we were cutting the canes when the potential was relatively high, and was for all different varieties of roses. So we proved that electrical potential difference between soilless plants is always negative. So plants have a higher potential than soil, and electrical potential decrease in a row from flower to leaf to stem. A lot more information is available in a new publication by Poznikov in Eurasian Soil Science in 2013. There it was proven that self-potential between a topsoil and a growing plant is highest in the spring, and then it decreases toward the fall when the plants are in Russia, in Moscow, ready for dormancy. Also, there are natural electrical potential between soil horizons or between layers of artificial growth media, and those potential influence plant growth. We artificially created a horizontal drift of electrical potential in soil with metal spikes at the middle row, and then we can see that onion would kind of curved over that potential, and the best growth was in the middle row, showing the highest potential difference. So in soils, we can also use self-potential measurements to create the map of subsurface water fluxes and find the potable places for potable water wells. Also, the electrical potential differences exist between soil horizons, and we used self-potential and electrical resistivity methods to detect clogged drains. If you know that the art of dosing goes back of thousands and thousands years, so basically it's nothing more than the sensitive person, the medium, kind of measuring the subtle electrical potential of the water flux under the ground. And if you go to the website of American Society of Dosers, it says that anybody can be a medium, but you have to be trained this ability. Well, the advantage of the Landmapper device is that everybody can use it, and it's measure very small fluctuation of electrical potential in the topsoil. So using that device, we found that place for that water well in Moscow suburb, and that actually there was a professional doser who first went around the area and also pointed to the both of locations. We choose that one. A lot of soils, as you know, have layers, and because of soil forming processes. And what the soil forming processes do, like process of alluviation, it leaches out the electrical charges down the soil profile and create the horizons different in electrical properties. In humid zone, there is alpha soils, mollisols, and histosols. And if we did measure different electrical potentials and electrical resistivity in those alluvial horizons, and alluvial horizons different texture, clay horizons and sandy, so we can see that resistivity, as according to the Ohm's law, is directly related to their electrical potential. The higher resistivity also implies the higher potential differences in those soils, and it's related with, of course, cation exchange capacity or humus content and so on. In New Jersey Pinelands, there is an area with alpha soils and very sandy soils, and they grow cranberry. What happens, if the drainage is not good enough, the production fields drops, and you can see it here is waterlogged conditions. So we did measure electrical resistivity map on the surface and also yields on the same cranberry beds. As you can see, that waterlogged situation has lower resistivity and has reduced yield and also has reduced electrical potential. Basically, those are the area where Phytophthora root rot develops and future worsen the yield. Basically, the condition was to put the drainage tranches there, because the drainage plastic pipe were actually clogging with bulk iron. So instead of putting another pipes, we suggested putting the coarse material in backfill. That's improved the situation. So moving on from electrical potential to DC methods of resistivity. As you see, that the Ohm's law show that resistivity is directly proportional of potential divided by current. In the methods of resistivity, they used four-electrode probe. The current is injected and measured between outer A and B electrodes, and the potential is measured with EMN electrodes, potential electrodes in the middle. They're different arrangement. And also conductivity is the inverse of resistivity, so basically that's the same techniques, although it kind of sounds like it's a different. So EC became very popular in modern agriculture, especially in the United States. There's a lot of companies like various technologies, Geonics, and our company. Also, those new technologies, new devices and equipment allow obtain fast, dense, and accurate GIS-compatible soil EC or ER, electrical resistivity measurements. Soil EC is related to several soil properties like bulk density, CEC, humus content, and it can be used to outline management zones. Also, the important difference of modern technologies of geophysics, they measure EC in the subsoil in different depths, and we can choose the depths which are more important for plant root growth. Depending on the plant, it can be deeper or shallower. Remote sensing, on the other hand, only measure spectral reflectance from the surface from the plant, so it doesn't get much information about soil. Also, on-the-go EC sensor measure soil EC non-destructively and in situ, and they use a big soil volume, so it's more accurate actually about to know about real condition in soil than a point soil sampling. And also, those sensors are very suitable for soil monitoring and time series because we don't collect samples. We can put the array on the top and measure different times of the year and reflect of water fluxes and different changes in soil profile. So there is a few different devices on the market now. I mean, they were developed, the four-electrode pulley, like a plowing things, was developed by USDA Salinity Lab and commercialized by various technologies. And this DC equipment is four-electrode probe or have two depths simultaneously, and maximum usually about 1 meter maximum depth for those techniques. There are also non-contact electromagnetic devices. There's ohm mapper that's used capacitive coupling. It's also like several electrodes, the same four-electrode principle applied, and there are 5 depths. And there is also multi-frequency electromagnetic devices, which are going deeper, not because of the spread of the electrode, but because of the different frequencies. It can be measured on 14 depths. And also maximum of AC equipment is usually about 10 meters. The small land mapper could be used instead of going in covering the whole field is very dense measurements. If you're only interested in some kind of trouble spots, you can quickly go and take point measurements with the land mapper, and also can be as deep as meter or even deeper than that if there needs to be. But for mapping in agriculture purposes, usually 1 meter is the most interested depth. Actually, the first foot is the most of interest to the growers. But important to consider is what kind of properties can we measure with electrical resistivity techniques. As I told before, those properties are directly related, influence density of mobile electrical charges. Can be chemical properties, first of all, as soil salt content, CEC, humus content. Also, if we have intrusions of high resistivity object in soil, like stones or oil, that can be mapped very precisely. Physical properties which influence mobility of electrical charges is bulk density, water content, temperature, texture, soil texture, and so we can monitor physical changes like water movement, soil freezing or melting, soil compaction or mixing. Most of techniques used in agriculture and precision agriculture is EC technique of mapping. I wanted to kind of show you the extension of this technique because other presenters will tell more about mapping of EC mapping in precision agriculture. I want to concentrate on technologies of vertical electrical zonding. The vertical electrical zonding is different from mapping. As you go from the one spot, you go measure multiple depths going down the soil profile. You can easily customize the sounding just through different electrode arrays, and also there is a lot of freeware available for 1D data interpretation. For example, the array or probe is 4 electrodes. In the Venerists you have equal distance between the electrodes. In Schlumberger you keep the potential electrodes in the middle, and then you spread A and B electrodes farther and farther apart. This way you're reaching deeper and deeper. And the coefficient for center symmetric arrays, like a Schlumberger, is calculated by the geometrical formula distances between electrodes. And so you can use a simple land mapper with custom wires, and you can spread the electrodes, and all the procedure is available on our website, so you can go and see how it's done in details. Then when you measure the profiles, you put the distance between A and B electrodes on their axis, and then it means it goes deeper when the A and B increases. So in this case we could see that vertical electrical zonding profiles in that Cranberry bed in New Jersey shows that the depths of about 1.5 meter we have an iron layer which showing increase in electrical resistivity, that bog iron layer. Also the same was shown in Russia, in Crimea, where we have several vertical electrical zonding profiles of stony soils, and they increase. So we developed it with showing that volumetric stone content and the electrical resistivity measured in situ, and how much rocks, and then the different orchard species was evaluated, how well they can tolerate the stony soil, and how to manage the orchards in that situation. Also, there, as I mentioned, that when the soil water freezes, it changes electrical resistivity dramatically. So when we set up the electrodes in the fall, and then in the spring when the snow started melting, we monitored how deep was the frozen layer. In this case, the frozen layer was very shallow, about 30 centimeters or so, and then every day measurement the value of resistivity changes, and then that's finally the whole profile on 16th of April was below 200 ohm meters. Also, that these VS profiles can show the drying depths on the peat soils, and it was a particularly dry summer when the whole first half a meter of peat soil was extremely dry versus when it's wet. You can see this profile here. And the same situation was in arid condition in the Volga Delta. There the sandy soils, but have a evaporation water condition. So in the groundwater table is about 2-5 meters. For the VS curve, you can see the twist to the kind of low resistivity, which is potable or salty water. In this case it's salty water. You can see very low resistivity. In this case it also changes, but the water is less salty. Also we can, it's pretty accurate method if you don't want to drill the borehole to find groundwater table. In first couple of meters we get about 8% error, VS versus real borehole data. Also, with vertical electrical zonding, it's pretty quickly to do because it's about 15 measurements on one spot. But also, some researchers use 2D and even 3D resistivity studies. They use multiplexing of different arrays. For 2D, for example, it's still possible doing manually, although you're talking about 800 data points for one study, so that can be difficult to do manually. Although some researchers in USDA used our device and kind of custom multiplexer to measure preferential water flow under the cornfield. There is also a lot of conventional geophysics equipment can be adapted for those studies. And those stationary DC equipment measure 3 electrical parameters: self-potential, electrical resistivity, and induced polarization. And different depths can be achieved through the electrode spacing and combination. And those equipment can be used in a lab to measure the same properties in the soil samples. Also, the multiplexing of four-electrode arrays is usually automatic. Those are websites from EPA, and you see the limits of different equipment. And for agricultural study, you don't need a very powerful signal. Actually, 2 microampere is enough. But there is available equipment, and for example, Cyber using 48 electrodes, and the whole system is about 18,000. Basically, since this equipment is can measure several properties, it's necessary to have a setup how to use it in agronomy survey. So we kind of suggested 7-step approach. First is that you need to select location of vertical electrical zonding based on the maps for the area. Then conduct vertical electrical zonding for the major soil and select the depths for the specific soil horizons. Then map area with 2-5 key depths and create the survey maps in GIS. Then get the samples and measure resistivity in the samples and soil properties in the lab. And then we can invert resistivity maps to the maps of soil properties. That's kind of quick overview. That's what we did in a field near Moscow. It was 90 VS test location and about 400 multi-depth stations. Basically, those are resistivity maps of different layers: 10 centimeters, 30, 60, and almost 5 meters. Then we measure soil properties in the lab, and of course there was exponential relationship between clay content and resistivity. There was coefficient of filtration, the water content, and the field capacity of those samples. Then the electrical resistivity at the deepest layer, presented here, was inverted into clay content map, filtration coefficient map, and a field capacity map. So, in the conclusion, you can see that resistivity and self-potential are complementary methods. We see resistivity and electrical potential outline density of mobile electrical charges in soil, and electrical parameters relate with amount and mobility of the electrical charges with exponential relationship. And often the same equipment can be used to measure EC, resistivity, and a self-potential with different accessory and electrodes. According to Ohm's law, again, resistivity is directly proportional to potential, and EC is inverse of resistivity. Self-potential in agriculture can be applied to monitor subsurface water fluxes and functionality of the drains, and also could be used to find placement for potable water wells. A natural electrical potential between soil horizons facilitate plant growth, and decrease in electrical potential difference between soil and plant indicate plant stress. However, we can create favorable potential difference in soils by media layering and applying weak electrical current of boring different metal spikes in soil profiles. EC methods in agriculture can be used to monitor one soil property which changes resistivity dramatically, like in freezing, melting circles, solution transport, or drying wetting. We also can map soil properties which highly influence electrical parameters, such as salinity, stone content, hard pan, oil pollution, groundwater table. And also we can evaluate complex effect of many soil properties on measured electrical resistivity. We can develop management zones or study soil cover structure. And at the end, as I said, that two techniques, potential and resistivity, are complementary, and there are devices which can be used to measure both. And this is a land mapper, which device is handheld, and you can go to Landviser.net and download publications and more information about methods and devices, and please contact us and we can help you with your project.